In 1948, Claude Shannon gave the modern world a price tag for surprise. Before him, information was a loose word. Bell Labs could measure voltage, bandwidth, noise, and relay cost. It could not measure the thing every wire was built to carry. Engineers knew messages differed. They did not yet have one unit that could count how much uncertainty a source produced before the message arrived. Shannon wrote the answer in one line. H of x equals minus sum over I of p sub I times log base 2 of p sub I. That line did not measure meaning, it measured uncertainty. A fair coin carries 1 bit. A fair die carries about 2.585 bits. A predictable letter carries less than a random one. Once uncertainty has a unit, communication becomes accounting. That accounting now runs compression, noisy channels, cryptographic randomness, and the cross-entropy loss behind next token prediction. The formula looks small because the hard work is hidden in the question. If information means meaning, the problem never ends. If information means choosing one message from many live possibilities, the problem becomes math. By the late 1940s, Bell Labs stood inside a new world. Telephone traffic was rising. Telegraphy still mattered. Radio had become a wartime tool. Television was coming. Early digital computers were leaving the lab. Engineers knew how to move signals. They did not know the general law behind all signals. A letter, a pulse, a voice wave, and a picture looked like different objects. Shannon saw that they shared one hidden question. In 1948, Bell Labs faced a costly bottleneck. Every mile of cable, relay, repeater, and radio channel had limits. Yet nobody could say the minimum number of bits needed to encode a source, or the maximum reliable rate through a noisy channel. Claude Shannon, then a Bell Labs mathematician, had to solve a practical problem. If the source makes messages faster than the channel can carry them, no code can save you. If the source can be compressed below the channel's limit, reliable communication becomes possible. Engineers had fragments. Harry Nyquist studied telegraph speed in the 1920s. Ralph Hartley argued that information should grow with the logarithm of the number of possible messages. Morse code gave short codes to common letters and long codes to rare ones. Those pieces were useful. They were not enough. Hartley's rule worked cleanly when all messages were equally likely. Real messages are not like that. English is not random. The letter E is common. The letter Q usually points toward U. After the qui, C is no shock. Before Shannon, the craft knew something the math had not yet owned. Common symbols should be cheap. Rare symbols should be expensive. Predictable structure should be removable. But no one had a general law. The stakes were not academic. The same missing law touched telephone networks, wartime cryptography, television, magnetic storage, radar, and the first computers. A bad answer wasted bandwidth. A good answer saved equipment, power, time, and money. It also drew a line that cleverness could not cross. Some messages can be compressed. Some channels can carry them. Some cannot. Shannon wanted the exact boundary. This was not one device problem, it was a system problem. A message begins at a source. A transmitter changes it into a signal. A channel corrupts it with noise. A receiver tries to rebuild it. A destination needs the result. If each stage uses a different idea of information, the whole system becomes guesswork. Shannon's genius was to ignore the surface form. A voice call, a printed page, a television frame, a radar pulse, and a stream of bits all become choices from a set. Some choices are likely, some choices are rare. The channel does not need to know what the message means. It needs to know how many live choices must be carried. That move made the problem hard and clean at the same time. Hard because real sources have structure. Clean because structure can be turned into probability. It also made Bell Labs the right place for the breakthrough. A university mathematician could have admired the problem. A phone company had to ship the answer. Bell had physical wires, switching costs, traffic loads, noise, repeaters, and customers. Every extra bit per symbol was not abstract. It was capacity that had to be paid for. This is why the theory arrived with such force. It did not begin as a philosophy of information. It began as a bill for uncertainty. The gap was this. Engineers needed one number that respected probability, added across stages, and told them how much uncertainty a source produced. Morse had already guessed the trick in wood and wire. Shannon turned the trick into a law. To get that law, we first need to meet the cast of characters inside the formula. A random stream can look like pure chaos. A short sentence can change a war. Claude Shannon found the ruler that separates surprise from signal. He gave engineers a way to count uncertainty in bits. That ruler now sits inside file compression, cryptography, networks, and machine learning. Before the symbols, fix the cast. Think of a coat check. The attendant must hand the right coat to the right owner. The hard part is not the coat. The hard part is the uncertainty before the choice is known. The first character is X. X is the uncertain source. It is the thing before you see the outcome. It might be a coin flip. It might be the next letter in a word. It might be a packet on a network. It might be the next token in a sentence. It is the unopened envelope. X is not the result. It is the state before the result arrives. The second character is the menu of possible outcomes. A coin has 2. A die has 6. A language model may face tens of thousands of next tokens. The third character is probability. Each outcome gets a share. A fair coin gives heads a probability of 0.5. A loaded coin might give heads a probability of 0.9. In English, the letter E is more likely than Z. Those probabilities must add to 1. That is the whole budget of the future. Together, they exhaust what can happen next. The fourth character is surprise. A sure event teaches you nothing. A rare event teaches you more. If Q is followed by U, you learn little. If Q is followed by Z, you learn a lot. You may even suspect the text is not English. The fifth character is the average. Shannon did not want one shock. He wanted the long-run cost of surprise. A file has many symbols. A channel carries many choices. A network runs over time. The measure had to work on streams. The sixth character is time. One outcome can surprise you once. A source keeps speaking. Entropy per symbol becomes bits per symbol. Entropy rate becomes bits per second. That is how a coin flip reaches a real network. The seventh character is code length. A common outcome should get a short code. A rare one can carry a longer code. That is why Morse code gives E1 dot. It gives Q a longer pattern. Entropy marks the best average code length any lossless code can hope to reach. Now the coat check earns its keep. If every coat is equally likely, the attendant needs many questions. If almost everyone brought the same black jacket, the next coat is easier to guess. Entropy is the average number of yes or no questions needed to identify the owner. That is why the formula travels well. The coat can be a letter, it can be a pixel, it can be a password character, it can be the next token in text. The math does not care what the object is. It cares about the probability spread. This also shows why entropy is not just a count of outcomes. A fair die has 6 faces. A loaded die also has 6 faces. They do not have the same uncertainty. The loaded die spends most of its life on one face. The fair die spreads its future across all 6. That difference is the whole point. Entropy measures the shape of uncertainty. It does not measure the size of the menu. Entropy is not a measure of how much stuff you have. It is a measure of how many live possibilities remain. Once the cast is clear, the equation can appear without magic. Here is Shannon entropy. H of x equals minus sum over I of p sub I times log base 2 of p sub I. Here, h of x is the entropy, or average uncertainty, of the random variable x. X is the uncertain source or event before the outcome is known. I is an index that runs over every possible outcome. P sub I is the probability of outcome I. Sum over I means add the term across all possible outcomes. Log base 2 of p sub I is the base 2 logarithm of the probability. which sets the unit as bits. Claude Shannon published this formula in the 1948 Bell System Technical Journal. The paper made the bit a working engineering unit. The empty meter now has a dial. It reads bits. The equation says one plain thing. Entropy is expected surprise. To see that, split the formula in two. First, define the surprise of one outcome. Surprise sub I equals minus log base 2 of p sub I. Here, surprise sub I is the surprise tied to outcome I. P sub I is the probability of outcome I. If P sub I equals 1, surprise is 0. A sure event tells you nothing. If P sub I equals 0.5, surprise is 1 bit. If P sub I equals 0.01, surprise is about 6.64 bits. Rare outcomes carry more surprise. They rule out more alternatives. Then average that surprise. H of x equals sum over I of P sub I times surprise sub I. Here, H of x is the average uncertainty of x. P sub I is the probability of outcome I. Surprise sub I is the surprise attached to outcome I. That is the whole idea. Weight each possible surprise by how often it happens. Then add the bill. Now run the basic cases. A fair coin has two outcomes. Each has probability 0.5. Its entropy is 1 bit. One yes or no question can pin it down. A loaded coin with heads at 0.9 has less uncertainty. Its entropy is about 0.469 bits. Most flips tell you what you already expected. The coin can still surprise you, it just does not do it often. A fair die has 6 equal outcomes. Its entropy is log base 2 of 6. That is about 2.585 bits. You cannot ask 2.585 literal questions for one roll, but over many rolls, that average matters. It tells you how short an efficient code can become. Now compare two 6-sided dice. The first die is fair. Each face has probability 1/6. The second die is loaded. It lands on 6 half the time. It spreads the other half over the other 5 faces. Both dice have the same menu. They do not have the same entropy. This is the first common mistake. People count outcomes and stop. Shannon asked how probability is spread across them. A world with many fake possibilities can hold less uncertainty than a world with fewer real ones. The pattern stays clean. Equal possibilities give the most entropy. Dominant outcomes lower entropy. Certainty kills entropy. That is why entropy becomes a floor for compression. If a source makes 1 bit of entropy per symbol, no lossless code can beat 1 bit per symbol on average. If the source makes less, then it has redundancy. English text has redundancy. Images have redundancy. Pure random noise does not. Shannon made this human in 1951 with printed English. People guessed the next character with more and more context. More context made the next character less surprising. That experiment is an ancestor of next token prediction. A modern language model plays the same game at scale. It sees context. It assigns probabilities to possible next tokens. The training loss punishes the model for giving low probability to the token that actually came next. That is Shannon's old surprise in new clothes. The unit matters too. A bit is not just a binary digit on a chip. It is the price of a binary choice. 4 equal messages need 2 bits. 8 equal messages need 3. 1,000,000 equal messages need about 19.93 bits. That one scale lets engineers talk across fields. One engineer talks about file size. Another talks about signal rate. A security engineer talks about key strength. A machine learning engineer talks about loss. The common scale is the deep invention. The coin and die are not toy examples. They teach the right habit. First ask what the source can do. Then ask how probability sits across those choices. Only then ask how many bits you must carry. If you can guess the next symbol, the source is not boring. It is compressible. The formula works, but why did the logarithm have to be there? The logarithm is not a flourish, it is forced. Start with equal possibilities. Suppose one choice has A outcomes. A second independent choice has B outcomes. Together, they have A times B outcomes. A sane measure of uncertainty must say this: f of A times B equals f of A plus f of B. Here, f is a candidate measure of uncertainty before Shannon fixes its exact form. A is the number of possible outcomes in the first choice. B is the number of possible outcomes in the second choice. A times B is the number of joint outcomes when the choices are independent. If this feels too neat, that is the point. The whole equation hides inside the demand that staged choices add the right way. Only logarithms turn multiplication into addition. That is why the log appears. If one relay doubles the possible states, it should add 1 bit. If two independent choices multiply the possible states, their information should add. Now bring back unequal probabilities. Real sources are biased. Some outcomes are common, some are rare. So Shannon turned the measure into an average. Each outcome contributes a surprise. Surprise sub I equals minus log base 2 of p sub I. Here, surprise sub I is the surprise of outcome I. P sub I is the probability of outcome I. Then the source pays that price with frequency p sub I. H of x equals sum over I of p sub I times surprise sub I. Here, h of x is the entropy of the source x. P sub I is the probability of outcome I. Surprise sub I is the surprise for that outcome. That gives the familiar form. H of x equals minus sum over I of p sub I times log base 2 of p sub I. Here, h of x is the average uncertainty of x. P sub I is the probability of outcome I. Log base 2 of p sub I is the bit-scaled surprise term for outcome I. In 1948, Shannon gave the demands in a tighter form. The measure had to change smoothly when probabilities changed. It had to grow when equal choices grew. It had to obey the branching rule. The branching rule matters most. If you break a choice into stages, the total uncertainty must equal the first stage uncertainty plus the expected later uncertainty. Continuity matters because nature does not jump when a probability moves by a hair. If a coin shifts from 50-50 to 51-49, uncertainty should shift a little. A jumpy measure would be useless. Growth matters because more equal choices should mean more uncertainty. A fair die should hold more uncertainty than a fair coin. A fair deck should hold more than a fair die. Any measure that fails that test is not measuring what engineers need. Branching matters because real systems work in steps. You do not send a whole language in one giant blast. You send letters, you send packets, you send frames, you send blocks. The measure must survive being cut into pieces. Think of a filing cabinet. First, pick a drawer, then pick a file in that drawer, or pick directly from all files at once. If the total uncertainty changes because you changed the path, the measure is broken. Entropy survives that test. Make it concrete. Suppose the first question chooses between two drawers. The first drawer has 2 equal files. The second drawer has 6. If you ask in stages, you pay for the drawer first. Then you pay the average file question inside the drawer you chose. If you ask in one step, you choose from all 8 files with their proper probabilities. A good measure must give the same total. That is why simple counts fail. That is why the raw number of choices is not enough. Probability must enter the formula. The measure must care that one drawer is more likely than the other. It must care that files inside each drawer may not be equally likely. This is why the equation feels found rather than picked. Shannon did not choose a handy statistic. He showed that if you ask for those properties, the form follows, up to a constant that sets the unit. There is one more gain. Entropy turns redundancy into a number. A random uppercase letter from 26 letters would carry log base 2 of 26. That is about 4.70 bits. Real English does not. Some letters are common. Some letter pairs nearly force the next one. Context lowers surprise. The gap between the raw symbol space and the true entropy is redundancy. For storage, redundancy is waste. For communication, redundancy can save meaning when noise hits the signal. That tension is beautiful. The same repeated structure that lets gzip shrink a file also lets a human read a sentence with typos. Shannon did not settle whether redundancy is good or bad. He priced it. The log is the toll booth between multiplication and addition. But the formula gets its power by refusing to measure one thing people keep asking it to measure. Here is the wall. Entropy measures uncertainty. It does not measure meaning. Shannon said this plainly in 1948. Semantic questions lay outside the engineering problem. His system had to reproduce a selected message at another point. It did not have to explain why the message mattered. That choice made the theory useful. If Shannon had tried to measure meaning, he would have sunk into philosophy. By measuring uncertainty, he gave engineers a tool they could use. But the boundary creates mistakes. Password strength is a clean case. A random 128-bit key has 128 bits of entropy if a trusted source generated it uniformly. A human password does not act like that. Humans choose names, they choose years, they choose keyboard walks, they choose song lines, they choose clever swaps attackers already know. NIST now warns about this. Entropy is easy to compute for a known distribution. It is hard to estimate for user-chosen passwords. Cryptography shows the same wall with sharper stakes. AES 128 may be strong math, but the number 128 only means what it claims if the key truly has enough unpredictability. That is why NIST Special Publication 800-90B exists. It sets tests and rules for entropy sources used by random bit generators. In 2008, Luciano Bello disclosed the Debian OpenSSL random number bug. A Debian patch had stripped key entropy from OpenSSL's generator. Many SSH and SSL keys made on affected systems became predictable enough that they had to be replaced. The cipher was not the weak point. The source of uncertainty was. Machine learning hits the same wall in softer form. Cross-entropy loss tells you whether a model gave high probability to the token that appeared. Lower cross-entropy often means better prediction. It does not prove understanding. A model can predict text well and still fail on truth. It can fail on cause and effect. It can fail on planning. Entropy can score surprise in a distribution. It cannot certify meaning. Markets make the wall expensive. A low entropy price path may look easier to predict. It may also be a predictable collapse. A high entropy market may be hard to forecast. It may still be safer than a crowded trade built on one story. The Bell Labs problem was to reproduce messages through channels. It was not to decide whether those messages were true, wise, or worth hearing. The useful rule is plain. Entropy is a governor, not an oracle. It can scale confidence. It can warn that a system has narrowed into too few paths. It can show when many holdings hide one shared story. But it does not create edge. The edge must come from somewhere else. That rule blocks a second mistake. High entropy is not always bad. Low entropy is not always good. A utility stock may hold less surprise than a biotech stock. That does not tell you which one is cheap. It only tells you how spread out the outcomes look. The same warning holds for models. Lower cross-entropy on a benchmark can mean better prediction. It can also mean the benchmark is narrow. It can mean the model learned shortcuts. Entropy can tell you how surprised the model was. It cannot tell you whether the model deserves trust. That is why this wall belongs in the middle. Without it, entropy becomes a magic word. With it, entropy stays a tool. A perfect random password has high entropy and no poetry. A line of poetry can have lower entropy and change a life. So what does this narrow ruler buy us in the real world? Here is the trade. By measuring uncertainty and not meaning, Shannon made the theory useful enough to leave the page and enter machines. Once engineers could price uncertainty in bits, they could design codes against a limit. They could ask how closely a real compressor approached the entropy of its source. They could ask how much redundancy to add before noise broke a message. They could ask whether a random number source was strong enough for keys. They could ask whether a model's predicted probabilities matched the stream it faced. That is the bargain. The ruler is narrow, the uses are wide. Start with compression. If entropy sets the floor, then every compressor lives in relation to it. Huffman coding, arithmetic coding, and later practical tools like zip all live on that map. They win because real data is not pure noise. Text repeats, images repeat, sound repeats. The source leaves clues. Entropy tells you there is room to squeeze. Now take communication. A noisy channel scrambles messages. Shannon's wider theory showed that reliable communication is still possible below a channel's capacity. Entropy sits at the heart of that result. It tells you how much uncertainty the source creates before the channel adds its own trouble. From telephony to satellite links to fiber networks, bits became the common language because Shannon gave them a meter. Then take cryptography. A cipher can only hide what the key does not already reveal. If the key source is weak, the whole system is weak. That is why good systems guard entropy at the source. They sample thermal noise. They sample timing jitter. They test random generators. They do not trust appearances. A key that looks random is not enough. It must be drawn from a source with real uncertainty. Now look at machine learning. Training loss in language models often uses cross-entropy. That sounds far from Bell Labs. It is not. The model assigns a probability to the true next token. The loss rises when the model acts surprised by what happened. Over billions of examples, engineers tune systems by that bill. Shannon's measure became the scorecard for prediction. The Bell Labs problem can now be solved in places Shannon never saw. We can move text, speech, images, and video across the world with error rates low enough for daily life. We can compress them enough to store them at scale. We can protect them with keys that are strong when the entropy source is strong. But the old warning still stands. No amount of entropy can tell us whether the message is true. The historical impact is plain. Modern compression standards, digital communications, and error-correcting codes all stand on Shannon's 1948 frame. Cryptographic practice depends on entropy estimates and on standards like NIST SP 800-90B to keep random sources honest. Machine learning now uses cross-entropy as a daily work metric, which ties one of the hottest fields on Earth back to a blackboard in Bell Labs. Shannon's hero was a small formula. It measured expected surprise in bits. That formula built the scale behind compression, secure key generation, digital networks, and model training. The thing to keep is simple. When you face a system that must guess, compress, encode, or protect, ask first how its uncertainty is distributed. Entropy is not a theory of meaning. Inside the problem it chose, it is one of the cleanest levers ever built. Entropy is the shipping weight of uncertainty. You can pack better. You cannot make the weight vanish. The first payoff is compression. Shannon's source coding theorem says a source with entropy, h bits per symbol, can be encoded near h bits per symbol. It cannot be encoded below that limit without losing information. That law sits under Huffman coding. It sits under arithmetic coding. It sits under gzip, zstd, Brotli, FLAC, PNG, and modern video codecs. Compression is not magic. It strips out what you could have guessed. The second payoff is communication. Shannon showed that a noisy channel has capacity. Below that capacity, reliable communication is possible with the right code. Above it, no clever trick wins. Every cellular standard works against that line. Every satellite link does too. Every Wi-Fi system does too. Every undersea cable does too. Engineers can spend more power. They can use more bandwidth. They can build better codes. They still answer to Shannon. That is why modern networks feel strange and clean. Noise never left. Fiber still fades with distance. Radios still interfere. Satellites still fight the long path through space. The win was not a world without noise. The win was coding close enough to the limit that noise could be handled. Shannon also split two jobs that people used to mix together. First, compress the source down toward its entropy. Second, code the compressed message so it survives the channel. Source coding and channel coding are different jobs. That split made whole industries easier to build. The third payoff is cryptography. Security is priced in bits. A key length means little unless the key came from real unpredictability. Entropy is the raw fuel that cryptography burns. The fourth payoff is machine learning. Cross-entropy loss is Shannon's idea turned into a training rule. A language model predicts a probability spread over the next token. Then the real token arrives. The model pays the negative log probability it gave that token. Over trillions of tokens, that cost trains the model. It is expected surprise. The system pays it again and again until it learns patterns in language. That does not mean the model understands the world as a person does. It means the training process found many patterns that cut surprise. That is still a huge thing. A system that cuts surprise across language can learn grammar. It can learn facts. It can learn style. It can learn code. It can learn weak hints about cause. But the loss itself stays plain. It asks one question at each step. How much probability did you place on the token that appeared? The fifth payoff is markets and decisions. A 2024 paper by Daniel Papla and Rafal Sedletsky studied 43 stock markets from 2007 to 2023. They found that entropy of prices and returns tended to fall during crisis periods. The lesson is not that low entropy predicts profit. The lesson is that compressed markets may be fragile. When many paths collapse into one script, market efficiency can weaken. A market can look calm while it grows more dangerous. This matters when a portfolio looks diverse by count but not by information. 30 tickers can still be one trade. They can all depend on the same rate cut. They can all depend on the same AI capital spending cycle. They can all depend on the same China recovery. They can all depend on the same liquidity wave. The list of names says many. The entropy of the story may say one. The reverse can also be true. A small set of positions can hold more useful information if the signals disagree in independent ways. One signal might come from valuation. One might come from balance sheet repair. One might come from industry momentum. One might come from insider ownership. If each signal fails for a different reason, the portfolio has more live paths. In a modern portfolio, Shannon's old ruler helps answer the Bell Labs question in another form. How much uncertainty is your system truly carrying? How much capacity do your bets have to absorb it? Shannon's 1948 paper did not just improve telephone engineering. It founded information theory. It set the laws of compression and channel coding. It gave security engineers a bit-based language for key strength. It gave machine learning the loss function that trains next token systems. The formula still runs through storage, networks, encryption, prediction, and portfolio risk. For Orion's world, this is why entropy belongs next to Kelly. Kelly tells you how much to bet when you have an edge. Entropy asks how stable the information behind that edge really is. If every signal agrees because the world is simple, concentration can be earned. If every signal agrees because they all share the same hidden input, concentration is a trap. Half Kelly is one practical answer to estimation risk. Entropy is another. If the edge is noisy, shrink the bet. If the signals are crowded, shrink the bet. If one story has quietly swallowed the whole portfolio, shrink the bet until real diversity comes back. Entropy does not choose the trade. It prices the not knowing inside the trade. The bit is a tiny unit. It is also a scale large enough to weigh the modern world. Shannon entropy is h of x equals minus sum over I of p sub I times log base 2 of p sub I, the average surprise of a source measured in bits. That one line built the working language of compression, communication, cryptography, machine learning, and uncertainty-aware investing. When a decision feels certain, write down the live possibilities, assign probabilities, and ask how many bits of not knowing remain.